These are going to be our notes that review the concept of inverse functions. So to kind of give us an idea or an introduction into inverse functions, if we take a look at this table, this is a table of data where the independent variable is time, and that's going to be measured in hours. And the dependent variable is going to be the population. In this case, it's a population of bacteria at that specific time. So this is a table, you've probably seen something very similar to it before. So for example, at 0 hours there were 100 bacteria, at 1 hour there were 168, etc. So what we say about this particular set of data is that n is a function of t. Meaning, if you want to know what n is, that's the dependent variable, that's the number of bacteria in the population, you would need to know the time as an input and get a population as an output. The way that we denote that in notation is we say n equals f of t. The other way you can also say that is that n equals n of t, or you can call it f of t. They have specifically denoted this as f of t, so we're going to use their notation, but another way you could have notated this was to say that n equals n of t. And the other thing that we notice is that this is in fact a function, and remember the definition of a function is that each input has to have a unique output. So for example, if you input a time of 2 hours, there can't be two possible number of bacteria at 2 hours. That's what makes this a function. Now what could happen is, let's say at 3 hours, instead of 358 bacteria, there were 259 again. Does this now represent a function? The answer is yes, it still does, because each input, meaning 2 and 3, have a unique output. If you input 3 hours, you don't have two possible outcomes. There's only one. So given all of that, imagine for a moment that this is not the information that you were actually interested in. Instead of being interested in an input of time in hours and an output of number of bacteria, what if instead we were actually interested in answering a question more along the lines of, when do we reach a population of, let's say, 400 bacteria? If that's the question that you're asking, you're no longer looking to find n as a function of t. You're now thinking of t as a function of n. You want to input a number of bacteria and output the time at which that population occurs. When you do that, what you're doing is called finding the inverse of that function. Now the notation for that is this f with a -1 in a superscript. That is not an exponent. That is not f raised to the -1 power. That's a superscript. It's just something to denote that you're looking at f inverse instead of f. So for us, that would say that t is f inverse of n, is the time required for the population to reach n, meaning the input is now the number of bacteria in the population, the output is now the time. That's the inverse function. You can find the values of f inverse by either reading from the table on the previous slide, but you'd have to read right to left, or this table is the same table, just the two columns have been switched. So for example, if we wanted to talk about f inverse of 550, now without looking at the table for a moment, keep in mind what that's asking. For a population of 550 bacteria, what is the time we should have? So for a population of 550, the time, the output for the inverse function, would be 6 hours, because of the fact that for the original function, when we input 6 hours, the output, the number of bacteria, was 550. So that's just an example to kind of introduce us to the concept of inverse functions. Now the thing to keep in mind, though, is that not all functions possess inverses. So let's take a look at some other examples. Let's compare the functions f and g, whose arrow diagrams are shown. Okay, so this one is your function f, and the bottom one is your function g. Just to kind of reacquaint you with some of the vocabulary, these are called the domain of f, and these are called the range of f. Here is the domain of g, here is the range of g. Okay, so we use words like For the function f, 4 maps to 10. If the input is 4, the output is 10. 1 maps to 2 for the function f. If the input is 1, the output is 2. Notice for the function g, 3 maps to 4 and 2 maps to 4. This is still a function. But notice that f never takes on the same value twice, meaning any two inputs in the domain have different outputs. G does. Both 2 and 3 have an output of 4. In symbols, what we say is that g of 2 equals g of 3, but for the function f, when you input any of the inputs, call it x sub 1, input it into the function f, it will never be equal to the output when you plug in an x value of x sub 2, whenever you're not plugging in that same x value twice. That's how we write it in mathematical symbols. So any function that follows this property, that f of x sub 1 does not equal f of x sub 2 whenever x sub 1 does not equal x sub 2, we refer to as a one-to-one function. Okay? One-to-one. The other way to write that would be a 1 and a colon and a 1. That's a shorthand way to write it. So you can either write it out 1-to-1 or you can write 1 colon 1. They mean the same thing. So a function f is called a one-to-one function. So first and foremost, it is a function, but this is also a one-to-one function. If it never takes on the same value twice, and there are those symbols that we just discussed, which are great as long as you're interested in the symbols. If you're more interested in looking at, say, a picture, a graph, and determining whether or not you're looking at a one-to-one function, what you're looking for is in your graph that anytime you input any two different x values, that you will never get the same output. And if you take a look at this graph, for example, if you plug in this x sub 1, you get this particular y value. When you plug in x sub 2, you get the same y value. That is not the graph of a one-to-one function, because I can plug in two different x's and get the same y. It is a function, but it's not one-to-one. So what we have then is a geometric method for determining whether a function is one-to-one. It's what we call the horizontal line test. And it says that a function is one-to-one if and only if no horizontal line intersects its graph more than once. This should sound a little familiar. If you remember the way we tell if a graph is a function, not a one-to-one function, but a function, we have a vertical line test. If I can run every possible vertical line through this graph and never hit the graph twice, then I'm looking at a function. Similarly, if I have a graph and I can run every possible horizontal line through that graph and I never hit it more than once, then the function is not only a function, but it's one-to-one. Now obviously this one fails the horizontal line test. Let's take a look at the function f of x equals x cubed. We know it's a function. We should know that from previous courses. The question is it a one-to-one function? And we have a couple different ways we can approach that. We can either say, look, no matter what x value you put in there, as long as it's not the exact same x value over and over again, when you cube it, you're going to get a unique number. I mean, 1 cubed is never going to be the same as 2 cubed, is never going to be the same as negative 2 cubed, for example. By definition, therefore, that function is one-to-one. The other way to go about it, and this one's usually preferable to students because you can visualize the results, is to look at the graph. So this is the graph of f of x equals x cubed. This is what we refer to as a basic shape graph. We do expect you to know what that is off the top of your head. And if you look at every possible horizontal line that you would run through this function, it will never hit the graph more than once. Therefore, this is a one-to-one function. The reason we bring up one-to-one functions is because those are the functions that possess inverse functions, according to our definition. So let f be a one-to-one function. So it passes horizontal line test and meets the requirements of those algebraic symbols that we mentioned. It has a domain of A and a range of B. Then its inverse function, which we denote with that f with the -1 in the superscript, has a domain of B and a range of A and is defined by, so here's how we define it, We're used to the stuff on the right-hand side, that y and f of x are the same thing. When you input an x into your function f, you output y. If its inverse function, f inverse, exists, then f inverse of y will be equal to x for any y in B. So the definition says that if f maps x to y, then the inverse function, f inverse, maps y back to x. And that's why you need these to be one-to-one, because if it weren't, then what would happen is when it maps back, it wouldn't be unique anymore. So if we had, here's a picture for you, if we had all these values, x's, and all these values, y, f would take x and turn it into y. F inverse takes that y and turns it back into x. Inverses undo each other. And the other thing to keep an eye on is that the domain of f inverse is the same as the range of f. When you have a function in its inverse, their domain and their ranges are switched. So to talk about that undoing process, the fact that the function and its inverse undo each other, if you take a look back at that f of x equals x cubed, the inverse function should undo the cubing. Well, what function undoes cubing? Well, cube roots do. And remember, x to the 1/3, that's the exact same thing as the cube root of x. That's according to rules of exponents, in case you don't remember those, that any base, any legal base, raised to the m over n is equal to the nth root of a raised to the m power. It's also equal to the nth root of a raised to the m power with the m on the outside. So it's either under the radical or outside. Traditionally, this is the easier one to work with, but they're both correct. So that's where I'm getting this. This is the cube root of x, technically to the first power, which of course we don't write. So again, that -1 that you're seeing here in the superscript is not an exponent. This does not mean 1 over f of x. If we meant 1 over f of x, we would have to put this -1 on the outside of that function in brackets. So when you see this, never mistake that for a fraction or for a reciprocal. It never means that unless you see the brackets. Okay, so let's look at an example. Let's say for a function, you knew that when you inputted 1, your output was 5. When you input 3, your output 7, and f of 8 is -10. Find the inverse function evaluated at 7, the inverse function evaluated at 5, and the inverse function evaluated at -10. So remember, when you're looking for the inverse function evaluated at a number, the idea is for the original function, this isn't an input. This is an output. So the question this is actually asking is, what x value did you input to the original function to get the output of 7? And if you look back here, that's going to be 3, because f of 3 is 7. So the inverse function evaluated at 5 is asking you, what did you input into the original function to get an output of 5? And if you look, that would be 1, because f of 1 equals 5. And then f inverse of -10 will be 8, because f of 8 equals -10. So for a question like this, for example, I couldn't ask you what is f inverse of 0, for example, because I never gave you, for the original function, what input gave you an output of 0. So this is not a question that I can ask for this particular one. Okay, so if we look at a diagram of how that occurred. So this was the original function. F of 1 was 5, f of 3 was 7, f of 8 was -10. Here's your inverse function that undoes what f did. It takes 5 and maps it back to 1. 7 maps back to 3, and -10 maps back to 8. So the letter x is traditionally used as the independent variable. So when we mostly don't want to talk about f, we want to talk about f inverse, we usually reverse the roles of x and y. And instead we say, okay, well then f inverse of x equals y means that f of y equals x. So that's so that we can maintain that tradition of using x as an independent variable. When we substitute for y in definition 2 and substitute for x in 3, we get what are called cancellation equations, meaning when you take an inverse function and you input into that the original function evaluated at some x, the output, when you apply both the function and its inverse to that input, your output is x. It's the same as the input for every x in A. And remember, A is the domain of f. That's the original function. Likewise, this is also a cancellation equation, just in a different order. For the second one, you input x first into an inverse function, and then you take the result and put that into the original function. These are both compositions. And the second one is true for every x in B. And again, B is the domain of the inverse function. It was the range of the original function, but it's the domain of the inverse function. Okay, so to get a little more concrete with this, take a look at the example. The first cancellation equation says that if you start with x and apply f, so x goes into f, the result of just that part is f of x. If you then take f of x and put that into the inverse function, f inverse, what happens is the inverse undoes what the original function did and just gives you back what you started with. They undo each other. And that's true regardless of the order. The only thing the order is going to affect is the domain and range. So for example, go back to that x cubed versus the cube root of x. These are inverses of one another. Well, watch what happens when you compose them. If you take x and plug it into f, which is x cubed then gets plugged into, here's your x cubed, gets plugged into the inverse function, which means you're now taking the inverse function in place and you put in x cubed in place of x. Well, what happens when you raise a power to a power? According to laws of exponents, a to the m raised to the n is a to the m times n. You multiply. And what is 3 times 1/3? It's 1. So sure enough, you come back to the input of x. If you go in the other order, if you put x in first into the inverse function, in which case this is now f inverse of x is x to the 1/3, and you plug that into f, you take x to the 1/3 as your input and you cube it. And again, you're going to multiply those exponents. And sure enough, you're going to get x again. So these undo each other when you put them in a composition. So that's great. That's actually how you can check if two functions are inverses of one another. But what we also want to be able to do is say, okay, if I have a function, how do I figure out what its inverse is if it's not obvious? I mean, if we give you a function like, let's say, I don't know, f of x equals x plus 2, I think you can probably tell me what the inverse function is going to be now that you know that inverse functions undo functions. So if the original function adds 2, then the inverse function is probably going to subtract 2. And sometimes it is that obvious, and other times it's not. So we want to have a step-by-step approach to actually being able to find inverse functions. So there's really two main steps in calculating an inverse function. You need to be able to solve for x in terms of y, and then you want to be able to treat x as the independent variable. So we'll switch x and y. So the steps are, you write y equals f of x, you solve the equation for x in terms of y, if that's possible, and then to actually express the inverse function as a function of x, you just switch your x and your y. Now, most of you, when you learned this in, let's say, a college algebra or a pre-calculus algebra class, you probably switched the order in these. We don't want to do that. In practice, you will get the same answer, but in calculus, the thing we're most interested in is solving that equation for x in terms of y. That's actually how we express what the inverse will look like. That's how we undo all the operations done. So let's take a look at a specific example. Find the inverse of f of x equals x plus 1 over x minus 2. Now this one is not nearly as obvious as the one I wrote on the previous slide. We're actually going to need to go through our steps. So if we start off with y equals x plus 1 over x minus 2, we want to solve for this in terms of x. So first I need to get rid of those fractions. So I'm going to have x minus 2 times y equals x plus 1. Now what I'm noticing, I'm going to go ahead and do my distributive property over here. I've got xy minus 2y equals x plus 1. Now this one's going to provide me with a little bit of a challenge, because if you notice, I have two x's in this equation, meaning that I have an x that shows up in two different terms. So for example, doing something like subtracting this 1 doesn't solve for x, because I'll still have another x to deal with. So the bad news is that complicates solving this for x. The good news is, if you know the trick, it's the same trick every time. You move every term that has an x in it to one side of the equation, and no, it doesn't matter which one. You move every term that does not have an x in it to the other side of the equation. And now what you'll notice is, because I've purposely separated the terms that have x's versus the terms that don't, what do the terms on the left-hand side now have in common? Well, they have an x in common, and if they have it in common, I can factor it out. So this becomes x times y minus 1 equals 2y plus 1. And if you notice, that eliminates my problem. I no longer have two x's that I have to work with, there's just one. Keeping in mind that the operation going on between the x and the y minus 1 is multiplication, we undo that using division. So therefore x is equal to 2y plus 1 divided by y minus 1. So that completes step 2. I have solved for x in terms of y. X is isolated, there are no more x's on the right-hand side. So then all I have to do is switch my x and my y. So I'll have y equals 2x plus 1 over x minus 1. That way x is my independent variable. And then also a lot of times you'll see us switch and say, okay, well then f inverse, if you write it as a function of x with x as an independent variable, that's 2x plus 1 over x minus 1. And so if you notice, that wasn't going to be obvious. It's not like you can look at this original function and say, of course I can tell exactly what its inverse is going to be. You have to go through these steps to figure it out. So the switching of x and y in the algebraic method of finding an inverse also tells us that we need to do the same thing when we're looking at the graph of a function. If we have the graph of a function and we want to know, well, what does the graph of its inverse look like, we can also switch x and y. And watch what happens when we do that. So let's say, for argument's sake, the point 0, 3 were on the original function, or the graph of the original function. Well, when we switch the x and the y, what ordered pair do we then know is going to show up on the inverse function? Well, we know it's going to be 3, 0, because we switched the x and the y. So when we graph them, here is 0, 3. And here is 3, 0. Those 2 points are technically inverses of one another. Okay, if we knew, let's say, 5, 1 was on the original function, then 1, 5 should show up on the inverse. So here's 5, 1, 5, 1, and 1, 5. Those 2 points are inverses of each other. Notice, though, what starts to happen when you start looking at points like 2, 2. When you switch the x and the y, it's still 2, 2. So you have this point here that when you look at both the point and the inverse of that point, it's in the same spot. It doesn't change. The same thing would happen if you had a point on there of, let's say, I don't know, 4, 4. Okay, when you look at its inverse, it's still 4, 4. So what we see happening is that when you look at a point on a graph and the inverse of that point on the graph of the inverse, they tend to start moving around unless they happen to have the same x and y coordinate, which means all of the points on the line that have the same x and y coordinate have something special going on. Well, we call that line the identity line. This is the line y equals x. That's the identity line. And all of the points that are inverses are actually flipping back and forth over this line. The reason you're not seeing it in the points where they have the same x and y coordinate is because they're already on the line over which they're flipping. So that's what we know about inverse functions. The graph of f inverse is obtained by reflecting the graph of f about the line y equals x. So if I had a function here, f, and I wanted to graph its inverse, all I would have to do is draw in the line y equals x and reflect it over that line, and that would give me the graph of the inverse function. And that's our review for this concept.